All right, welcome to another week of physics. I am trying um, a new camera, so hopefully the quality is even better. Let me know. Sound too, let me know how that works. This lesson is lesson 3 for magnetism, and it is on magnetic force on a conductor. It's not a long lesson, the math is fairly plug and play as well. So we'll go through the PowerPoint together. All right. Okay, so not yesterday, the previous lesson, we learned that there's a magnetic force on charged particles that are moving through a magnetic field. Now, this is true, except in a couple cases. If that charged particle 1 is not moving with respect to the field, then there's no charge. You have to remember the formula QVB. Okay? Fm equals QVB sine theta. So if V is 0, there's no force. Okay, so you can have a charged particle in a magnetic field that feels no force. It just simply can't be moving. Also, if the particle is moving parallel to the field, so theta is 0, well then sine of 0 is also 0. So in that case as well, the particle will not feel any magnetic force. Now if we have a bunch of particles, say, moving through a conductor, and that conductor is put into a magnetic field, well then all those charged particles will feel a force, and they'll apply that force onto the conductor that they're moving through. So that's what we're going to go over today. So you can look at the picture below. So here we have an example of current. Notice positive to negative. We're doing conventional current. Goes through a magnet with magnetic field going north to south. Okay. The current's going this way. You can use your right-hand rule because we're doing conventional current. Put your thumb in the direction of the current, your index finger in the direction of the field, and you should get your middle finger pointing down. Now, if you were to switch that current, then you should get your middle finger pointing up. Okay, usually I like to do a demo of this, but I don't have my equipment, so I am going to post a YouTube video from MIT on the classroom, which is a great demo of this, so take a look at that. And there's our right-hand rule. All right, so let's figure out what this would look like. Now, if we were to rewrite this equation, now obviously we don't have one charge, we have n number of charges, lots of charges. But that's hard to count. If you look at a conductor, you don't just look at a conductor and start counting how many electrons they're flying past, even though they're moving quite slow. You still don't want to count them. That's a lot. So let's look at the definition of current. Well, current is defined as the number of charges passing by some cross-sectional area in some time t. So we can write the equation for current as the number of charges passing through a cross-sectional area in time t. We can rearrange that to solve for Q. What we can also do is look at the basic definition of speed and say speed is just distance over time. Now, if it's a wire and you have a charged particle moving through that wire, well, then distance is just the length of the wire divided by the time it takes to go. Now, these two equations, 2 and 3, I can put back into our original equation. And some great things happen. One, n is going to cancel. This is great. We don't have to count how many charged particles there are. Not only that, time cancels. Well, that's great too, because there's no way I'm going to be able to measure the time it takes for any one charge to move through that conductor. And we're left with Bill. Yes, F equals BIL. Magnetic field times the current times the length of the wire. Okay, times by the sine of theta, which is the angle between the current and the magnetic field. Okay, and that's pretty much it for the lesson. I'm going to just rearrange this, and now, yes, I'm finally going to define what a Tesla is. So if we rearrange this and solve for B, we get that 1 Tesla is the magnetic field strength when you have a conductor with a current of 1 amp and a length of 1 meter moving through a magnetic field at an angle of 90 degrees will experience a force of 1 Newton. So in SI units, 1 Tesla is 1 Newton per amp meter. Now we know what a Tesla is finally. So let's try this question. This is the first question on the back of your handout. I don't think I need to write it all out. You're just going to use our equation bill. And look, I'm writing it out anyways. B-I-L sine theta. You don't even need to rearrange it. It's just asking for the magnetic force at 3 different angles for those same values of B, I, and L. So I have those here. You can try and punch that in on your calculator. Now A and C is easy. Sine of 90 is 1 and C sine of 0 is 0. And then B, well, sine of 45 is, well, you can punch that in your calculator or just do 1 over root 2, I think. Or root 2 over 2, whichever you prefer. All right. Okay. Now on the back of your handout, I also write a couple other equations. You do not need to, let me make this bigger now. Okay, I put a couple of things on the back, those 4 up there. You do not need to know these, but these are Maxwell's equations. They describe everything there is to know about electricity and magnetism in 4 simple equations. Okay, now this is actually, you've done calculus, so you've done derivatives. This is not simply delta written upside down. Well, it is written upside down, but it does not mean what we usually just do, final minus initial. Okay, it is a differential in 3 dimensions of space over time. Okay, and we're not doing that. But definitely look at the descriptions I've wrote for the 4 equations. Okay, you don't need to know how to apply them or how to calculate them, but it's fascinating to look at them and understand what each one says. Remember, an equation is a story. It explains something. So the first one says an electric field has some sort of charge density. Okay, well, that we know. An electric field comes from a charge. The second one says that there are no magnetic monopoles. That I've gone over as well. You can't just have a north pole by itself. The third one says that a changing magnetic field produces an electric field. And vice versa, the fourth one says a changing electric field produces a magnetic field. And this is something really cool that they discovered. I mean, Michael Faraday thought that his fields, his ideas of fields that were going around a wire or moving out from a magnet, right? He thought these fields were static, which is understandable when you play with a magnet and iron filings. The iron filings aren't like moving constantly in a loop or anything like that. They're just in one place. But his math skills weren't very good because he had no formal education. But he had an interesting idea. He thought electricity and magnetism were the same thing and that they were actually light. But of course, without the mathematical background to prove it, at this point in his career, everybody thought he had just gone kind of crazy. Except for Maxwell. Maxwell was a Scottish physicist, and he came from a rich background and had very good education and very strong math skills. And he loved the ideas of Faraday's lines of force, which we call fields. And he used his mathematical skills to come up with those 4 equations. And those 4 equations showed that these fields are real, but not only are they real, they're not static, they're moving. Now, if you were to create a magnetic field, just make some sort of disturbance in a magnetic field or an electric field, doesn't matter. That disturbance of a changing magnetic field then produces a changing electric field. That changing electric field produces a changing magnetic field, which produces a changing electric field, changing magnetic field, changing electricity, and it just goes click, 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 back and forth between electricity and magnetism. And then using these equations, and we're not going to go over derivation, but using these equations, you can get that the velocity, that's backwards, the velocity at which that electricity clicks into magnetism, clicks into electricity and magnetism, the velocity at which that clicking propagates through space is equal to the square root of 1 over these other two constants, right? We have mu naught, which is the magnetic constant, also called the permeability of free space, which we'll get to in another lesson, and epsilon naught, which is the electric constant. And if we plug in that equation, just like they did 100 years ago, more than 100 years ago, they got that as the speed, which is exactly equal to the speed of light. So Maxwell and Faraday proved that electricity and magnetism is light, that light is an electromagnetic wave. And this is the first time, it's the end of the 19th century, so the late 1800s. This is the first time anyone actually finally knew what light was. And there was a question that was driving physicists crazy for hundreds of years, and now we finally knew. All right, so that's the end of that lesson. Like I said, short, couple easy questions. Okay, tomorrow we'll move on to the next lesson, which is Ampere's law. Ampere's great. I love that lesson. It'll be fun. We'll see you tomorrow.